Blockchain has come a long way in the last 10 years. With a lot of innovations in the system, it's truly becoming a revolution over time. So the thing that started the revolution was Ethereum with the introduction of smart contracts. And this was mostly revolutionized because Ethereum had very network-specific languages to actually develop these smart contracts. Hi guys, this is Arya, and today's video is all about discussing one of these Ethereum-specific coding languages, and that is Solidity. So before we actually go with the video, let's see the topics that we are going to cover today. So we're going to start off with discussing about smart contract programming. Then we're going to see the different smart contract languages that are available for us to program on Ethereum's network. Next, we're going to see into what is Solidity and why Solidity has become so famous over time. Drilling down further, we're going to discuss the Solidity tools that are actually used for developing code, and then we're going to get into the weeds of actual Solidity programming. Then in the end, we're going to build our very own smart contract that simulates a lottery with all the concepts that we learned throughout the entire video. Okay, so let's get going. So first of all, you guys must realize that Ethereum had a very key feature that it could implement smart contracts. Smart contracts being business logic that can run on the blockchain. So this means that the blockchain's realms were open to a lot of more services and fields like gambling, property transfer, which can be easily simulated with code. But the problem was that this code had to be run somewhere. So for that reason, the Ethereum virtual machine was made. So on the Ethereum virtual machine, only very specific languages can run. And these languages are Ethereum specific development languages. So out of all the languages, let's see some of them. So as you can see on the screen out here, the three most popular languages are Solidity, Serpent, and Triple L. So let's start with Triple L first. So Triple L is based on Lisp, which is another language for programming, and it stands for Lisp-like language. Triple L was one of the first languages that was actually built for running smart contracts on Ethereum because of its very minimalistic features and lightweight, which makes it very suitable for running on the Ethereum virtual machine. Second that got really popular was Serpent. So Serpent is influenced by Python and uses a .se extension after its file. It was pretty popular a while back, but due to security breaches, it has now been deprecated in use. At this moment in time, the most extensively used contract programming language is Solidity. Solidity is influenced heavily by JavaScript and uses a .sol extension. And as I said, it's one of the most popular things that Ethereum developers are using nowadays for actually coding their smart contracts. So let's look into what makes Solidity so popular. So as you guys can see, the definition of Solidity is that Solidity is a contract-oriented high-level language for implementing smart contracts. It was influenced by C++, Python, and very heavily by JavaScript, and is designed at targeting the Ethereum virtual machine. So many of you must be asking at this point that why can't we actually write our contracts in languages that we are familiar with like Java or Python? So you guys must remember that all this code is running on Ethereum virtual machine, which can only decipher Ethereum virtual machine specific bytecode, which is also known as EVM bytecode. Now EVM bytecode has to be very lightweight as this whole thing is running on a virtual machine and not some exact hardware. So for that reason, we have invented Ethereum specific contract languages like Solidity. So first of all, Solidity is statically typed. So that means that your compilation is not happening as you're typing. There's no interpreter running on the background that is actually running and checking your code for errors. It's something like Java where you write your whole code and then compile the file instead of something like Python where your code is constantly being checked by an interpreter that is running in the background. Secondly, Solidity is a high-level language. That means it is written in a very specific syntactical manner where it's not just machine code that the machine can understand. Anybody with a good knowledge of programming and Solidity can easily read and understand Solidity code. Above that, it is contract-oriented. So contract-oriented means that it is very lightweight in feature and can be easily compiled and converted to EVM bytecode, which is understood by the Ethereum virtual machine. So moving on, let's see the tools that are actually used for developing Solidity code. So as every language out there, you always need a text editor. So text editors like Atom, Sublime Text, and Visual Studio Code are excellent for Solidity as they have excellent support for Solidity syntax highlighting and source code editing. Above that, to actually compile your code locally, you need the SOLC compiler. Now this compiler can be easily installed with the use of Docker or the Node.js package manager known as NPM. So code editor and compiler go hand in hand and you're ready to go. Now there's actually another option for those of you who actually don't want to go through the trouble of actually installing a compiler and then a text editor with all its packages for syntax editing and source code editing. And that other option is called Remix. So Remix is an online IDE for Solidity. Now Remix can be also installed locally, but it is very much used as an online version. So just like every IDE, it is meant to actually improve productivity and take less time to actually compile your code. So let me just open Remix and show you guys why it's so popular. So as you guys can see, Remix has a very intuitive UI. It has a very clean looking text editor where you can go and type in your code like this, and it'll get automatically compiled. You don't need to actually go ahead and install a compiler on your own and go through the troubles of actually setting the environment variables and all that stuff. Next, you can actually run and deploy your smart contracts on various environments and account settings. Like out here, I'm using the injected Web3, but you can also use some external Web3 provider or a JavaScript virtual machine. Secondly, there's also this nice debugger that you can use to actually debug your code by block number and by transaction indexes or hashes. It's a really cool thing once you start actually using it and developing Solidity code. Now coming back to our session, I hope I made it clear that Remix is the best way to go if you're a beginner and you're trying to learn Solidity. Okay, so now that we've actually seen why Solidity was invented, how it is coded, and all the tools that are used in this development process, let's begin actually learning the language. So the first topic that we're going to start with is the structure of a contract. So as you guys can see here, I've shown you guys this very simple structure of a smart contract when written in Solidity in this gray box out here. So we begin by actually specifying the compiler version, which is set by the pragma keyword. Then we start defining our contract, and this is simply done by giving the contract a name with the contract keyword. Next, I've shown you guys how you can write comments and multi-line comments. A well-commented piece of code is always appreciated because it is very well understood by others and it becomes really easy to work in an organization. So you should always be very specific about commenting your code. So let's just run this very small piece of code on Remix. So as I said, to specify the compiler version, we go pragma solidity, and the up caret means that anything above what we specify, so 0.4.17. So our code will be actually compiled by any compiler version that is above 0.4.17. So next we have to define our contract, and this is done by actually just saying contract and then the contract name. So I'm going to name my contract demo. And then I told you all how to write multi-line comments and single line comments. So single line comments are just like this. This is a single line comment, and this is a multi-line comment. So that's the basic structure of a smart contract. Any smart contract, however complex it is, will always begin like this. So moving on, let's move ahead with operators. So most of the operators used in Solidity are very similar to JavaScript. As you can see, like JavaScript, we have three types of operators. Those are comparison operators, bitwise operators, and arithmetic operators. Comparison operators are of course used for comparing two values. Bitwise operators are used for bitwise functions like AND, OR, NOR, or XOR. And arithmetic operators are used for arithmetic. So let me just show you guys a quick example of arithmetic operators and bitwise operators. So we're just gonna use this thing that we made out here. So let's just create a very simple bitwise operator demo first. So let's call this bitwise, and I'm gonna do all the basic bitwise functions. So first of all, we actually have to specify two variables with the size of 1 byte, and that is done with the bytes keywords, and then you just specify the space by saying 1. So it's bytes 1. So you go bytes 1a is equals to 0xb5. So the 0x is just to state that we're typing our thing in hexadecimals. So this actually stands for, if I'm correct, stands for 10110101. So if you were to convert this hexadecimal, this would be the binary representative. Next, we need another variable to actually do our comparisons with, rather bitwise operations. So we go 0x, we'll say 56, and this probably stands for, if I'm not wrong, 01, 0, and 10110. Okay, now we're going to have 3 or rather 4 operations. We're going to do AND, OR, XOR, and NOT. So we're going to use the functions, and I'll explain how functions work later on in this video. So just catch up with me for now. So bytes 1, or A comma B, and then byte 1, example 3, XOR A comma B, and bytes example 4, which is not, and we're just going to pass it one argument. I'll explain why I just passed one argument into not and two arguments in the others. You'll understand in a short while. So let's make up the functions that actually will do our stuff. So function so I just copy pasted the functions to make my life a bit easier. So let me just explain to you guys what I've actually done out here. So we've declared two variables and we've assigned them hexadecimal values which are of 1 byte size. Next we are actually doing four functions. For the first function we are doing AND, then we're doing OR, then we're doing XOR, and then we're doing NOT. Now if you're actually not well versed with what these functions do, I actually suggest you go and look them up on Google. So the first function AND will return the AND between A and B. So it'll AND both these two binary numbers and actually return the value. Second, we have the function OR and will return the OR between A and B. Next we have XOR, which will return the XOR between A and B. And next we have NOT. Now NOT is a bit different out here, as you can see, because there is no actual support for negation in Solidity at this moment. But you can actually do this arithmetically, because doing negation is basically XORing your number with the hexadecimal 1. So that is 0xFFFF. So if you just do that, you'll get the negation of any number that you put in. So let's actually run this thing and see the output that it gives us. So we change the thing to JavaScript VM and we deploy our thing. So as you guys can see here, we have four functions made. Now let's deploy each and every one of them. So first we declare AND. So as you guys can see here, after clicking deploy, we have these four functions that we can run. So in the functions, we have to give the input parameters and we'll see that we get the output. Now, suppose I were to put the parameters into AND. Always be sure you put double quotes around your parameters as they are JSON representations, and then we go and run AND. So we get our output out here. And as you can see, that the decoded input was 0xb5 and 0x56. And the decoded output when both are ANDed is 0x14, which is hexadecimal 14. Now we can do the same for NOT, and we'd get the results for NOT. So if we also run the same thing for NOT, we'll get the same results. So you go and press it for NOT, and you see that our decoded input was 0xp5, and when you NOT it, you get 0x4a. You can do the same thing for OR. Just go and copy paste the parameters, run OR, and you see that we have ORed our two inputs and we get the result out here in the decoded output. We can also do the same for XOR. Click XOR and you get the output. So this is basically how bitwise operators work. Next thing on our list was arithmetic operators. So let's go and make a simple contract just for this thing. So we're going to call our contract a simple calculator, and we're going to be doing some very stupid but very simple transactions. So let's say we have two things, a uint A which equals 5, a uint B which equals 6. Now we're going to do all sorts of functions on this. So uint sum would be equals to A plus B, uint difference would be equals to A minus B. Now if you want to divide it, division between two integers will always return an unsigned integer, and it will probably floor it to the closest value. We'll see when we run this. A by B. Then we can have a product, and that'll be A star B. And we can also take out the remainder with the modulus function. So as you can see, it's compiled. Now let's just try running this simple thing that we've actually created. So we deploy it. Oh, I need to give this functions to actually give me some view of an output. So let me just quickly convert this into functions. So yeah, I kind of quickly just converted all my things into functions so that we can actually have an output situation. So now our contract is called the simple calculator, and we have those two very basic variables, which is a equals to 10 and b equals to 5. Now we've done 5 functions that are the 5 arithmetic operators. We've done the summation, we've done the difference, we've done product, that is multiplication, then we've taken out the quotient, which is the division, and then we've also taken out the modulus, which gives us the remainder. So this is just done by passing two variables into a function that is known as add, which returns a uint. So we've returned a plus b from the addition function, we've returned a minus b from the difference function, we've returned a divided by b from the division function, a multiplied by b in the multiplication function, and in the remainder function we are returning a modulus b. So let's deploy our contract and let's see how it works. So as you can see out here, we have 5 parameters. So now that we've actually deployed our calculator, let's see how it works. So let's first test out the add function. So we click on add, and it should add a plus b for us. So the answer should be 10 plus 5, which is equals to 15. So as you guys can see, the decoded output was 15 indeed. Next we try division. So division should give us a by b, which is 10 by 5, and the output should be 2. So as you guys can see out here, the decoded output of our division function is 2. Let's check out the remainder function because that seems to be interesting. So we try for the remainder function, and this should give us that. So once we run the remainder function, you guys can see that it gives us a remainder of 0, which is exactly what it should give, because when you divide 10 by 5, you get no remainder. So let's actually change the variables and see once. So we make it 6 out here, and then we run the remainder thing again. So now this time we should get 4. So if we change our variable to 6 out here instead of 5, and then we try the remainder again, you can see that it should return 4. And that's exactly what it returns. So now that we've seen bitwise operators and arithmetic operators, it's time we move on. So next on our topic is data types. So we have a bunch of data types to cover, so let's go through all of them one by one. So as you guys have seen already, there are 2 types of integers. There are signed integers and unsigned integers. Now all these integers are declared with their spaces within steps of 8. So like you can declare an int with 8 bytes and it'll be int 8. Then it'll go on increasing from 8 to 16 to 24 to 32 up till 256. And this also followed for uint, which stands for unsigned integers. Now the declaration of an integer value can be done with the int keyword or the uint keyword. It's followed by the variable name and then a value. For example, we define uint called marks and we assign it to the value 39 in this manner out here. Next, we have Boolean values. Now, as I said, Boolean values are of 2 types. They're either true or false. They're declared using the bool keyword followed by the variable name and then actually specifying whether the Boolean is true or false. For example, out here, we have a Boolean called pass and it has been assigned to true. Also, if you all remember, I had told you all that logical operators always return Boolean values. So things like and, logical and, or and logical or, even negation and equality and inequality all return Boolean values. So next on our list is fixed point numbers. Fixed point numbers are not fully supported by Solidity yet. They can be declared but cannot be assigned to or from. Signed and unsigned fixed point numbers are of various sizes. The keyword uFixed followed by m cross n, where m represents the number of bits taken by the type and n represents the number of decimal points that are available. It's really important to note that m must be divisible by 8 and goes from 8 to 256 bits, while n must be between 0 and 80 with inclusive of 0 and 80 both. Unsigned fixed integers and fixed integers are aliases of uFixed 128 cross 18 and fixed 128 cross 18 respectively. Next on our list we have address type. Now address type is very specific to Solidity as we need to specify the address of everything or every component that is residing on the blockchain. So we declare them by actually saying address, then the address's name, and then the value. So the address is normally a hex code which can be seen out here, like the example address home and then the hex code address value. So the address member also has some very important functions. So we can check the balance of any address by just calling address.balance. Then we can also send some money to some address by using the send function, and then we can also use transfer. Send and transfer both do the same things, but it's always recommended to use transfer, and this is why. So if a transaction fails when you use send, the transaction failure can go to a call stack depth of 1024, and it also fails the recipient run of gas. So in order to make safe Ether transfer, always check the return value of send, use transfer, or even better. So basically, send has a lot of security issues. So if a transaction fails midway, there is no possibility or no guarantee that the state will be rolled back to the previous one where you had all your money. This means you can potentially lose a lot of money if you're using send. So that's why with more updates, the Ethereum community came up with the transfer method, which has no such security issues. So next on our list of data types, we have strings. So strings in Solidity are stored in the UTF-8 encoding. Due to this reason, strings consume a lot of space on Ethereum virtual machine. And because of this, strings are completely avoided or used as least as possible, as they consume a lot of gas for their execution. Instead of strings, the usage of bytes for such variables has always been promoted by Ethereum developers. But just in case you want to know how you can use strings, you can just declare a string by going with the string keyword, then the variable name, and then the value. Now strings must be surrounded by double quotes or single quotes, it doesn't really matter. So as you can see out the example here, I've defined my name with the string keyword, with the name of the variable being name, and my name Arya. Okay, so the last type of data types that we're going to discuss is enumerators. So enumerators are a neat way in Solidity to create custom data types. So as you can see out here in the example, we have created a custom data type called a jet state. So it has 4 members, that is takeoff, land, autopilot, and still. So you can make your custom enumerator by the following declaration method. It started with the enum keyword, with the name of the enumerator that you want to specify, and then the members. It is very important to note that every enumerator must have one member at least. Okay, so let's try out a simple enumerator on Remix. So we're going to say contract enum, and it is going to create a simple enumerator. I'm going to show you how to do this. So suppose we were creating an enumerator for game choice. So you could actually have a few game choices like keep playing, pause. You can say pause, or you could say disconnected, or something like reconnecting. So these are just very arbitrary members to a game choice that makes no sense. But let's show you how you can make a game choice type. So you go game choice, and suppose you want to make a default game choice. So suppose you were playing GTA on a decentralized network. So the default game choice would be keep playing. So you would say go game choice dot keep playing, and that's how you would initialize a game choice type of data. So it's very simple, as you can see. Okay, now we have a lot to cover, so let's move on quickly. So next on our topic is data structures. So the first data structure that we're going to actually discuss is arrays. Now the use of arrays is very similar to that of JavaScript. Like JavaScript, we have 2 types of arrays, static and dynamic. Now static arrays have their index size or the array length always specified, while dynamic arrays do not have any specified length and are stored in the memory. So you can also create multi-dimensional arrays using syntax that is very similar to JavaScript, and it's shown out here. So you can go double square brackets and you can choose the index length, or you can create a dynamic array which is also 2-dimensional by just keeping these 2 blank. Moving forward, structs in Solidity provide a way to define new types in the form of struct. It is not possible for a struct to contain a member of its own type, although the structure itself can be the value type of a mapping member. The restriction is necessary as the size of a struct has to be finite. So as you guys can see here, we have created a struct called player, and we have 4 members of the player thing. So the 4 members are name, stats, age, and mortality, and these 4 members are each of different data types. So structure of player is a complex data type consisting of 4 member data types. So the next thing we have is data allocation. So data allocation is pretty important from an Ethereum point of view. So every complex type like arrays and structure has an additional annotation called data allocation about whether it is stored in memory or in storage. Depending on the context, there is always a default, but it can be overridden by appending either storage or memory to the type. The default for function parameters include return parameter, is memory, and the default for local variables is storage, and the location is forced to storage for state variables. There is also a third data location called call data, which is non-modifiable, non-persistent area where function arguments are stored. Function parameters and of external functions are also forced to call data and behave mostly like memory. Data locations are important because they change how assignments behave. Assignments between storage and memory also to a state variable always create an independent copy. Assignment to a local storage variable only assign a reference though, and this reference always points to the state variable even if later is changed in the meantime. On the other hand, assignment from memory stored reference types to another memory stored reference types do not create a copy. Okay, so the next type of data structures is mapping. Mapping types are declared as with the mapping keyword, then the key type, and then the value type. Here the key type can be almost of any type except for a mapping in itself, or a dynamically sized array, a contract, an enumerator, or a struct. The value type can be actually any type possible, including mappings itself. Now mapping can be seen as a hash table which are virtually initialized such that every possible key exists and is mapped to a value whose byte representation is all zeros, a type's default value. So the similarity ends here. The key data is not actually stored in mapping, only it's actually stored in a 𝐂𝐶_CAK256 hash table while it is looked up. So because of this, mapping do not have a length or a concept of a key of value being set. Okay guys, so now that I've explained mapping, let me show you guys a quick example of how mappings work in Solidity. So let's head over to Remix first and let's begin. So we say something like pragma solidity contract. So example of mapping. So we'll first create a mapping of which address, and it points to a uint, and we'll call these balances. Now we can have a function to update these. So as you guys can see, we don't actually have a counter and we have to actually do it all manually using a function. And there you go. You have an example of a very simple mapping. Now let's move ahead. So next we have function types. So as you know, like JavaScript, Solidity also has support for functions. Functions are generally used for code reusability and for actually shortening our code in a modular way. So the definition of a function is pretty unique for Solidity. It starts with the function keyword and the function name. Then you actually specify the parameters that you're passing into the function, if any. Then the visibility specifiers are discussed. Then the function modifiers are put in. And in the end, you must specify the return type with the returns keyword. So in our example here, you can see that we've made a function called 𝐒𝐽𝐻. Now the parameters that are passed in are the round index and the subport index, which are both uint type. Then the visibility specifier is selected to public, the modifier is selected to constant, and the return type has been specified as a boolean. So let's see what this visibility specifier and function modifiers actually are. So there are 4 types of visibility specifier: private, public, internal, and external. So when something is private, it is only visible inside the current contract. If it is public, it's visible externally and internally both. While internal things are visible only internally and external things are only visible externally. So one might think, why not just use internal whenever you're using private, and why not just use external whenever you're using public? Well, it's actually a good idea to use external over public when you know that your data is only being referenced outside your contract. In that way, you can be more secure and always consume lesser gas. Then we have function modifiers. Now Solidity comes with 4 pre-made function modifiers. Those are pure, view, constant, and payable. So pure functions are ones that cannot read or modify the state of a function. It is just a function that actually just accesses the data. Now then we have the view modifier, which means that the function can only view the data types of that contract. It cannot change the data types. Next we have constant for state variables, which disallow engagement. And last but not the least, we have the payable modifier, which allows a function to receive ether. Next, we can also build our custom function modifiers. So modifiers can be used to easily exchange the behavior of functions. For example, they can automatically check a condition prior to executing the function. And these modifiers are inheritable properties of contracts and may be overridden by derived contracts too. So this is the declaration of a normal modifier. So we declare our modifier with the modifier keyword, then we put in the mod name, and then we put our logic of the modifier. In the end, we have to put this underscore and semicolon to say that the function that the modifier is used after shall be passed if only the modifier remains true. So suppose out here we have an example of a modifier. So we say that the modifier is owner. So this means we require that the message sender has to be the owner. If it's not the owner, this underscore part will not be actually executed. So we have a function called withdraw money, and this can be only done by the owner. So the parameters sent are in this function is the uint amount, and isOwner is the function modifier. So before the function withdraw money is actually committed, this isOwner modifier will be checked. If this is actually true, then and then only will the function withdraw money will be committed. Moving on, we come to error handling. Now, Solidity has a very special type of error handling. Solidity uses state reverting exceptions to handle errors. Such an exception will undo all the changes made to the state in the current call and all its subcalls, and also flag an error to the caller. The convenience function assert and require can be used to check for conditions and throw an exception if the condition is not met. The assert function should only be used to test for internal errors and to check invariants. The require function should be used to ensure valid conditions such as inputs or contract state variables are met, or to validate return values from calls to external contracts. If used properly, analysis tools can evaluate your contract to identify the conditions and function calls which will reach a failing assert. Properly functioning code should never reach a failing assert statement. If this happens, there is a bug in your contract which you should definitely try to fix. There are two other ways to trigger exceptions. The revert function can be used to flag an error, and the revert the current call. It is also possible to provide a string message containing details about the error that will be passed back to the caller. The deprecated keyword throw can also be used as an alternative to revert, but throw is not normally used because it consumes all the gas that has been used in the current state. Next, and the last topic of our day is control structures. So, like JavaScript, even Solidity has control structures, and they're mostly very similar. So, aside from the support for the control structure switch and goto, Solidity has support for all the control structure that are there in JavaScript. So we have the if statement, we have the else statement, we have the ternary operators, then we have the break statements and the return statements and the continue statements. Also for looping, we have the for loop, we have the while loop and the do while loop. So now that we've learned all these concepts, it's only time that we start building our own first very smart contracts using what we learned today. So let's start building. Okay guys, so it's time we implement all the concepts that we learned today into a big smart contract that we're just going to create. So just hop into Remix and code along with me to actually practice everything that we learned. Okay, so let's first head over to Remix. So I already have that open, but as you guys already might know, you can always visit Remix by just going on remix.ethereum.org. So once you've been on Remix, go and press the plus button out here, and we're going to give our contract a name. So let's call it a demo. So what our contract is going to do, it's pretty simple actually. We're going to create a few getters and setters, which are actually very simple. So these getters and setters are going to be for instructors that are working in my company, that is Edureka. So suppose Edureka wanted to run on a blockchain system somewhere down in the line. So we could just simulate it using something very similar. So let's get started. So first things first, let's create a contract. Actually, first we have to specify the compiler version. So pragma solidity 0.4.18. Okay, so let's get on creating our contract. So contract Edureka. So first of all, we're going to have a bunch of instructors working in our company that teach all these courses. So let's create a struct for these guys. So struct instructor. So the instructor is going to have a name. Let's give him an age first. So he's going to have a name and the subject he teaches. Now we need to map all these instructors to an address. So we do that, as you guys know, by creating a mapping. So our mapping is going to get mapped from an address to all the instructor type data that we're going to have. So we do that by saying address pointed to the instructor, and we're going to call this instructors. as it'll just count all the instructors for us. Next, we actually need an array for all the instructor acts. So we'll just create an array of addresses. So it's going to be dynamic, as we just don't know how many instructors we're going to have. And let's call this instructor act. So these are all the instructor accounts, right? Now let's create an event. Event instructor info. So events are actually triggered when you're showing something on the UI. So instructor info, and we're going to show the name, the subject, the teachers, and the age. So this is our basic event. I'm sorry, it's not curly brackets, it's normal brackets that we use out here. Okay, so now we need a function to actually set the instructor. That's a very important aspect. So this will be a good practice of functions. So function set instructor. So while setting the instructor, we're going to pass down the address. We're going to call the address addr, and then we're going to pass down the age. So event age, the subject. Sorry, that's bytes. And his name. So we have a variable called instructor, and it'll be all instructors. And then you pass in the address of the instructor that you want to set it to. Next, we just go instructor.age, and instructor.name will be equals to the name. So now we successfully set up our instructors setter, which will actually set the age, the subject, and the name of the instructor. Next, we need a few getter functions. So what do getter functions do? They get the info that we've just set it. So we go function get instructor. So since we are only reading for values, it's going to have the view modifier. So that's a very good use of the view modifier that we just learned in this tutorial. So, and now this is going to return the address. So address, it's going to return instructor accounts. Return instructor. So that's done. Now we need, so this is only when we're not passing in any argument. So what if we actually pass in the argument of an address of an instructor? So let's create a getter for that too. So instructor. So this shows you all that when two functions have the same name, they get compared according to their parameters, just like here. Even this is going to be view, going to be public too, and it's going to return basically the same thing almost. Returns the age, the byte, and another byte. So basically out here, the uint that is going to be returned out here is the age, and the 2 bytes are the name and the subject respectively. So we need to return instructors address.age. So let's just copy this, quicker execution, return the age, the name, and the subject. So this is also a very good example of returning multiple values from a function. Now we can also have a function to count all the instructors. So let's make that too. So count instructors, view, public, and it's going to return a uint, which is basically the length. So it's going to return instructors dot length. Instructors is this thing. So mappings don't have lengths, so you have to return the instructor accounts.net. And there you go, you have your contract set up. So let's try putting some custom modifiers into this also. So suppose we only wanted the owner of this thing to actually be able to run this thing. So let's go contract owned. It's a new contract for us. And let's store the address of the owner somewhere, and function owned. So we set the owner to the message sender. I'm sorry, we've spelled owner out here. So owner is the message sender, And basically then we have to create our modifier that we used to apply. So modifier only owner, and let's see how we can do it. So should check that the message sender is the owner, so we'll go for a require. So require message.sender equals to owner. Don't forget to put the semicolon so that your function gets executed, and you're done. So now we actually need for this to be owned. Okay, so we're done. So we implemented a structure of a contract. We implemented custom modifiers. We saw the visibility specifiers. We used mappings. We used structs. We saw the different kind of functions that we can create, a view function and a normal function. And we also saw how to return multiple types of values from one function in itself. So this is how you can create a really simple smart contract for actually practicing everything you learned in today's video. So let's just give it a run once. So for running our thing, go on the Run tab and you just click Deploy. So as you can see, we have our set instructor function ready. So we can pass in the address out here. Then we could just give them an what else do we have to pass? Let me just give it a quick check. Address, then the age, the subject. So the age, let's make him 45 years old. Subject, he teaches blockchain. And his name is Arya. So now we set the instructor. As you guys can see here, our instructor has been set. And that's how you do it. So basically, that was it from me. So let's get back to the video for once. Before I actually end, let me tell you guys about Ethereum course on Edureka. So we at Edureka teach Ethereum in a very structured and modular way. We'll make you go through the beginner level topics like Blockchain 101 and to advanced topics like basics of Solidity and decentralized application development. Edureka is an online training platform with live instructor-led sessions. At Edureka, we also have a 24/7 support team that is there to guide you through your technical and non-technical issues related to your course. When you sign up for a batch at Edureka, you are given access to the learning management system, which contains all your documents, all your PowerPoint presentations, and even the classes that you've actually missed out. Secondly, if you're not satisfied through go-through of a course at Edureka, you can always sign up for future batches for completely free of cost. And above that, for any other questions that you have regarding the course, there's always the Edureka community where you can post your questions freely and get answers from technical experts. So that's it from me, guys. I hope I was successful in teaching a bit of Solidity to you, and I hope you all practice a bit more Solidity at home. That's it from me. Goodbye.